thank you everybody. I'd just like to start by thanking Duncan and friends at Sofian for the invitation today. So I'm going to focus on kind of some of the story that Liz has touched upon there and look at this family of channels that are called P2x receptors and talk about a collaboration I was involved with in the development of P2x3 antagonists, and also look at some positive allosteric modulators of some other P2x receptors that we've been working on. So firstly, I'd just like to touch on introducing purinergic signaling in P2x receptors. So we've heard quite a bit today about ATP being released by cells, and the family of purinergic receptors sit mostly on the cell surface to receive this message from ATP or one of its breakdown products, depending on what type of receptor you are. But the receptors I'm going to focus on today are the inotropic arm of this purinergic signaling system. So these are the P2x receptors. They're non-selective cation channels. They depolarize cells. They elevate intracellular calcium. And they're quite unusual structurally when we look at some of those other more familiar ligand-gated neurotransmitter type receptors. So P2x receptors have this double transmembrane topology, and they form as a functional trimer in the plasma membrane. So they have quite an unusual topology and stoichiometry compared to other channels. So the topics I'm going to touch on today are my collaboration with Merck and the development of P2x3 antagonists for refractory and unexplained chronic cough. And I'm also going to talk about some unpublished work looking at the endothelial P2x4 receptor and looking at ligands to augment its activity and develop some novel vasodilators. So I'm just going to introduce a little bit here about cough and why we're interested in P2x receptors. So cough is a helpful, normal physiological response, and it starts through these sensory neurons that are embedded within the airways wall that communicate with the central nervous system to elicit this motor reflex. So we've got sensory neurons carried by the vagus fibers out here in the airways, sensing the environment. And the neurons that are the sensory innervators of this tissue, their cell bodies are found in the nodos and in the jugular ganglia, and I'll lead on to this a little bit later. But so acute cough is obviously a normal and helpful response, but in chronic cough is a very debilitating, unmet clinical need. And in adults, it's defined as a cough that lasts for more than 8 weeks. It's a cough that is intractable to the standard of care treatment. And it accounts for about 10% of respiratory referrals to secondary care and estimated to have a large prevalence globally. So it's a big economic and social burden and an unmet clinical need. And more evidence points to some cases of a refractory and unexplained chronic cough as being due to some sort of neural dysregulation, something happening in these sensory pathways. So this brings me on to talk about what we term in physiological terms as a hyperreflexia. So that normal reflexive response has become, through some mechanisms, pronounced. And indeed, this is what's believed to happen in chronic cough, some cases of chronic cough, that you get this chronic neural dysregulation, but also in some types of incontinence or bladder hyperreactivity. So there's a link between this reflexia and some of the purinergic receptors that I'm going to talk about. So why think about purinergic receptors in any of these responses? Well, some work from Alan Maurice's group at the University of Hull, he's a cough expert, looked at the tussive effects of inhaling ATP. So when human subjects inhale ATP, this causes an increase in cough frequency. So that tells us that there's some receptors in the airway that are responding to ATP and can elicit this cough reflex. And you can get this concentration-dependent increase in healthy subjects, but people who suffer from chronic cough are more sensitive to this ATP inhalation. So some information telling us about the importance of ATP and coughing in humans. But what about those receptors that are there to sense ATP? So the main receptor that we became interested in was the P2x3 receptor. This is a rapidly desensitizing receptor. When you look in various body parts, you find it in sensory neurons almost exclusively compared to other tissues. And in here we're showing some staining patterns in the mouse, so in one of those nodose ganglia, which are the cell bodies from those sensory afferents coming up from the airways. And you can see P2x3 expression in some of the cell bodies expressed there. Also, if we look in the lumbar region in the dorsal root ganglia, we can find P2x3 expression. Predominantly, but not exclusively, in those small fibres which are the unmyelinated C fibres. So P2x3 is expressed in these types of neurons, and indeed its expression is retained if we culture neurons from these nodose ganglia and make recordings from them. So this collaboration with Merck started with a high throughput screen of small ligands against P2x3. And the hit that came out of this screen was the antibiotic trimethoprim. So trimethoprim is an approved antibiotic, and it's used predominantly to treat urinary tract infections. But through a series of potency and selectivity screens looking at derivatives of trimethoprim, this was the lead compound that came out, which was named MK7264. So it's only a slight chemical variant on this molecule, and we became interested in this molecule and trying to understand its effects on P2x3 and the P2x3 heteromer. So in patch clamp studies, we used human cell lines stably expressing human P2x3, and we can elicit these very rapid responses typical of homomeric P2x3, and we can then spray bath perfuse on some of this MK compound, and you can see that we very readily get an inhibition against the human P2x3 homomer. Also, if we stably co-express P2x2 and 3 in these cells, that we can see significant inhibition of these currents also in response to bath perfusion of MK7264. When we look at the potency of this compound, it's good. It's a very potent, nanomolar potent compound that blocks with an approximate IC50 of about 150 nanomolar, but it's not great in being not great in selectivity between P2x3 and 2,3. There's a nominal window, but it's very small. And if we look at the mechanism of action of MK, what we can see is that MK acts as an allosteric modulator of P2x3, here showing the effect on the dose-response curve here, elicited by the agonist alpha-beta methylene ATP. So MK7264 is a potent P2x3 receptor antagonist, but it can't select between the P2x3 homomer and the 2,3 heteromer. We also undertook some electrophysiology to understand how the drug acts at the channel, and we undertook some protocols to look at perfusing the compound when channels were closed compared to fast co-application when the channels were open. And these experiments I'm showing you here are all for the 2,3 heteromer. So you can see that if you elicit a response, an inward current, and then apply MK, you can get a very nice inhibition. But that's not the case if you try and do the same experiment when the current is on. So this is when the channel is in the open or in the desensitizing phase. So if we apply alpha-beta methylene ATP very rapidly and then rapidly switch to co-apply MK at the same time, you can see a very subtle inhibitory effect on that response compared to the vehicle control. And we can quantify these different wash-on times and look at these open and closed channel protocols, and we can see that the drug washes on very quickly onto the closed channel, but very, very slowly when we apply using this type of protocol. So this suggests some favouring of the drug for the channel in its closed versus its open state. And the human P2x4 receptor was crystallized with this drug bound. And their structural work complements what we've seen. So we know now where this molecule binds on the human P2x3 receptor. And the site that's available for binding is available in the closed channel state and poorly available in the open channel state. So what's believed to happen in terms of the mechanics of these P2x receptors when they become activated? They bind ATP up here in these head domains, and that when ATP binds, the receptor undergoes this conformation where you get this kind of clamping down of this head region. And the allosteric inhibitor, the MK compound, sits underneath here and inhibits this ability of this head domain to move down, thus opening the channel. So some structural work that supports the idea that the MK7264 binds preferentially to P2x3 when it's closed. We also looked a little bit more at what MK was doing at the homomeric P2x3 receptor. And in addition to seeing a robust effect on the peak current, what we saw at higher concentrations of MK is that actually you could get quite a pronounced slowing of the desensitization. We don't fully understand why this occurs, but we're very interested in terms of looking at where the drug binds and that transitional conformation of the P2x receptor. So you can see here, if we're measuring the tau, the time constants of desensitization, that when you get up to higher concentrations of MK, you can start to see this slowing of desensitization. Whether this effect of the drug is via the same binding site, we don't know. But this is a cough project, but the problem when you use mice and rats is that they don't cough. So they don't have a formal cough reflex, unlike guinea pigs, which are a very useful model for cough. But here, remember that P2x3 is also expressed in the dorsal root ganglia, so these are sensory neurons that can sense pain. And here we've looked in vivo and tested the ability of MK to reverse some inflammatory pain phenotypes in rats. So you can see this is CFA hind-paw injection in rat models. And then we're looking at the sensitivity of the paw to the von Wrey filament withdrawal, either in response to vehicle or the positive control, the non-steroidal inflammatory naproxen. So you can see that both MK and naproxen can alleviate this hypersensitivity in the von Wrey test. Also, if we look in the same models, rather than doing withdrawal, if we look at weight bearing, so look at the distribution on those hind limbs, the inflamed versus the non-inflamed, that you can see that in vivo application of MK, the P2x3 antagonist, can reverse these inflammatory pain phenotypes. So good evidence that MK can work in vivo. So this is a lot of the preclinical work that we were involved in. MK is not a very interesting name, but it was renamed as gefapixant, and this was in honor of Professor Jeffrey Bernstock, who is the grandfather of purinergic signaling. So unfortunately, we lost Jeff a couple of years ago, but this really does carry his namesake on forever, let's hope. So well done to Jeff. Importantly, this after the preclinical evaluation, this advanced under the name of gefapixant into the clinic and had some very encouraging phase 2 data looking at cough frequency and looking at the ability of gefapixant to reduce cough frequency. And you can see here that compared to placebo, that actually gefapixant is particularly potent in the subcategory of patients that are these very high frequency coughers. And this was reported in the Lancet. Liz touched on these cough 1 and 2 trials. So they showed through their trial information that there was a significant reduction in chronic cough, and they looked at 15, 45 milligrams, 12 and 24 weeks. Although it was effective in cough, there was this ongoing reporting of dysgeusia, which is this taste disturbance associated with taking gefapixant in these trials. But the trials progressed, and gefapixant is now approved as a drug in Japan, and it is now currently used as a new drug for treatment of chronic and unexplained cough, and it's the first P2x receptor antagonist to get through to approval. And we're still keeping our fingers crossed about the FDA, but hopefully all will be good by next year. So let's see what happens. And the molecular basis for some of these taste effects are because P2x3 can heteromultimerize. Remember, I told you at the beginning that they're trimers, so they can be homomeric, but they can also be heteromeric in nature. So they can mix and match with some friends to form some new flavors of channels. And if we look at the distribution of P2x3, this is in sensory neurons that innervate taste buds. So ATP, as we heard from the first talk this morning, is the neurotransmitter that allows those taste buds to communicate with these gustatory sensory nerves. The postjunctional receptors for these nerves contain at least P2x3 and probably contain 2 as well. So many of these taste effects are due to inhibition of purinergic receptors on these taste buds. And it's not clear, really, because we don't know about the molecular basis of P2x receptors in these sensory afferents, whether true and pure selective P2x3 receptor antagonists will get around this problem. But there's a number of compounds that have kind of come through in the wake of gefapixant, and a lot of companies had P2x3 receptors in the drawer through pain studies that got put away and then came back out when there was this cough interest. So Bayer had their eliapixant compound, which looked good, performed really well in phase 2, but has now been discontinued. We've got Shionogi's compound, which looks great as well, and that's currently got through its phase 2 development, and also the Bellis blue compound. So these are all, at least these 2, are following up, hopefully, into phase 3 trials for cough. Next, I want to just touch on some preliminary data. What I want to share with you, some of our interests, looking at a different P2x receptor and looking at P2x4 and modulation and its potential cardiovascular benefit. So we're very interested in allosteric modulation of P2x4, and we're interested in identifying novel allosteric sites. So looking at homology models of the P2x4 receptor, looking at what sites might become exposed when the receptor's moving between its open and closed conformation. And we've used these sort of techniques and rational drug design to identify some novel positive allosteric modulators of the human P2x4 receptor. And we're interested in this from a cardiovascular point of view, because P2x4 is heavily expressed within the vascular endothelium that lines all our blood vessels. And there's some hints from the literature that P2x4 is important in blood pressure regulation, because some humans have loss of function polymorphisms in P2x4, and this is associated with elevated pulse pressure. We know that P2x4 knockdown abolishes shear stress, induced calcium responses in vascular endothelium. And also when we look at the P2x4 knockout mice, they're hypertensive and they have reduced evidence of nitric oxide production. And that's where we think that P2x4 is having its role, where it's sitting in these vascular endothelia, and that in response to shear stress, so the flowing of blood across this layer of endothelia, that this leads to ATP release and activation of P2x4, elevation of intracellular calcium, and activation of eNOS. So we want to, and are developing, positive allosteric modulators to do that. So we've started to trial some of these using a technique called pressure myography. So in pressure myography, and this is a mesenteric artery that is cannulated and pressurized, and it's a very good technique because it allows you to luminally flow things through. So we've started to trial some of our positive allosteric modulators in these types of assays. So here we can see, here's the diameter of the vessel, and we measure that in real time through video capture. And we can see with this thromboxane mimic that we can contract up the artery. And then when we move from a no flow to a luminal flow condition, you get this flow-dependent vasodilation, which is symptomatic of that shear stress response on the endothelium and generating nitric oxide and causing the vessel to dilate. And there's evidence of that because if you use L-name to inhibit eNOS, that you do the same sort of protocol and you really dampen this shear stress mediated dilation. So if we start to introduce some of our P2x4 positive allosteric modulators into the assay, hopefully what you can see is that the vessels constrict up as normal with these thromboxane mimics, but now the response to shear stress is hugely augmented in these types of assays. So there's some real promise that we can target P2x4 in vascular endothelium with some of these positive allosteric modulators and enhance endothelial function in these types of assays. We're doing this in mice at the moment, but we're also starting to look in human small arteries. So I just want to finish here and thank everybody who's contributed in my group to these studies. I particularly want to thank Anthony Ford, who was at Afferent and led Afferent before they got bought out for gefapixant by Merck. And Anthony's been a real senior leader in driving P2x3 as a cough target. And thanks to UKRI, AstraZeneca, Merck and BHF for funding our work around this area. And so with that, I say thanks very much and happy to take questions.
Hello? Can you hear me?
I can, yeah.
So Derek Bowie from McGill University. With the MK compound, did you ever test if it's voltage dependent?
So we never tested its voltage dependence. So we don't have any information about that.
Yeah, see the speeding up that you see? It looks like open channel block.
Yes.
And then you get a prolongation in burst length.
I think that would make sense.
I think it's probably voltage dependent.
I imagine you'll be right.
Check out.
Yeah.
Martin Gunthorpe. Now you have the clinical data. I wondered if you have analysed it in a way which would allow you to say how much P2x3 inhibition we actually need to see to get a clinical effect, and whether you think there's any separation between that pharmacology in human and that versus taste.
Yeah, it's difficult, and as Liz was pointing out, cough is very complicated, and I think the different trials, it's hard to look between them because of the different cohorts, and Bellis actually had an horrendous initial phase 2, but then realised in their phase 2b they could look at those very high frequency coughers and see effects. So in answer to your question, it's complicated to know, and I think it's complicated to separate those taste disturbances from efficacy on cough. For gefapixant, I think they're always going to be there. You can't dose it out, and it's a trade-off, I think, between how tolerated it is if you're a very high-frequency cougher, whether you're happy to live with a little bit of taste disturbance.
But as a quick follow, I mean, do you think it's a partial inhibition, or do you think the free concentrations achieved in the airways are likely to be consistent with needing pretty much full inhibition of that channel to see an effect?
Yeah, it's difficult to understand because I imagine we don't know what is the molecular basis of the P2x3 out there and the relevant stoichiometry of that receptor. And gefapixant kind of binds just a bit at the kind of the interface. So it really matters what is the composition of that 2-3 receptor and the relevant stoichiometry. But I think partial inhibition would be enough to give you some of these adverse effects.
Thanks.
All right, thank you very much for